Under the theory of repulsion field, why do planets in a stellar system revolve around their central star in a totally different way from galactic spiral arms revolving around their central black hole? Let's take a look at this stellar system on the left-hand side with 4 planets, and a galaxy on the right-hand side with 2 galactic spiral arms. The 4 planets revolve around the central star with different angular speeds. Of the 4 planets, the innermost planet revolves around the central star at the fastest angular speed, but the outermost planet revolves around the central star at the slowest angular speed. Different from these 4 planets, the entire 2 galactic spiral arms revolve around the central black hole at the same angular speed, regardless of the distance from any star, in the galactic spiral arms, to the central black hole. What causes this difference? This video will provide the detailed answer to this question by adopting the theory of repulsion field. It makes sense that, in a stellar system, for example, the solar system, the inner planets must revolve around the central star at faster angular speeds than the outer planets, because the gravitational force can be considered as the only force that the central star exerts on its surrounding planets. The closer the distances from the planets to the central star are, the greater the gravitational forces that the central star exerts on them are. For example, Mercury takes 88 Earth's days to complete a cycle around the Sun, because Mercury is the closest planet to the Sun, and the Sun exerts a very strong gravitational force on it. However, Mars, the 4th planet from the Sun, takes 687 Earth's days to complete a cycle around the Sun. This is because the gravitational force that the Sun exerts on Mars is much weaker than the gravitational force exerted by the Sun on Mercury. In other words, planets of a stellar system revolve around their central star at different angular speeds to fight against the gravitational force exerted by the central star, and to prevent themselves from falling into their central star. Also, gravitational force is almost the only interaction force exerted by central stars on their surrounding planets. However, for a galaxy, it is believed by the theory of repulsion field that the interaction forces between a star in a galactic spiral arm and the central black hole are not only gravitational force, but also repulsion force. These 2 interaction forces that a black hole exerts on its surrounding stars, the gravitational force and the repulsion force, are almost cancelled out, leaving the stars being almost without interaction force exerted by its central black hole. Therefore, it is not necessary for stars in a galactic spiral arm to revolve around their central black hole at different angular speeds, like the revolution of planets around their own central stars, to prevent themselves from falling into their central black hole. The repulsion force, exerted by the central black hole, may be greater than the attraction force, and even repels its surrounding stars. This explains why galaxies are expanding. So, what is the theory of repulsion field, and how does the theory of repulsion field make the difference? There are 3 important details of the theory of repulsion field that make this difference. First, under the theory of repulsion field, it is believed that, if pure neutron matter, the matter that is made of 118 chemical elements and can be found everywhere on the Earth, is put in conditions of extremely high temperatures and pressures, like those at the centers of black holes, stars, including the Sun, such pure neutron matter will be converted into rich neutron matter. And the reverse also holds true. If pressures and temperatures of a rich neutron matter body is lowered, for example, if it is no longer surrounded by pure neutron matter for some reason, such rich neutron matter will be converted back into pure neutron matter. The conversion from pure neutron matter to rich neutron matter does not release energy, but the conversion from rich neutron matter to pure neutron matter releases massive amount of energy. This is the way that the Sun and other stars generate energy and shine. Second, the bigger a heavenly body is, the higher the percentage of rich neutron matter it contains. The smaller a heavenly body is, the lower the percentage of rich neutron matter it contains. Extremely big heavenly bodies, like black holes, contain a very high percentage of rich neutron matter at their cores. For example, more than 50%, let's say, from 50% to 80% of their masses is rich neutron matter. Medium heavenly bodies, like stars, contain a fairly high percentage of rich neutron matter at their cores. For example, less than 50%, let's say, from 20% to 50% of their masses is rich neutron matter. Finally, small heavenly bodies, like planets, contain a very small percentage of rich neutron matter at their cores. For example, much less than 50%, let's say, 1% to 5% of their masses is rich neutron matter. Third, bodies of rich neutron matter produces repulsion field in the surroundings, and this repulsion field, in turn, repel the surrounding bodies of rich neutron matter. The repulsion field is similar to the gravitational field in its nature, but it works against the gravitational field. Gravitational field is produced by poor neutron matter and it attracts the surrounding bodies of poor neutron matter. Meanwhile, repulsion field is produced by bodies of rich neutron matter and it repels the surrounding bodies of rich neutron matter. Gravitational field does not interact with bodies of rich neutron matter. The reverse also holds true. Repulsion field does not interact with bodies of poor neutron matter. No instrument nor laboratory apparatus that is made of poor neutron matter can measure any property of rich neutron matter, even the mass of rich neutron matter bodies. Let's take a galaxy that includes only a black hole and a star, for example. Assume that the total mass of the black hole is m sub b, and 70% of the mass of the galaxy is rich neutron matter. Also, assume that the total mass of the star is m sub s, and 30% of the mass of the star is rich neutron matter. The product of the mass of poor neutron matter of the black hole and the mass of poor neutron matter of the star is 30% times m sub b times 70% times m sub s, which is equal to 21% times m sub b times m sub s. Meanwhile, the product of the mass of rich neutron matter of the black hole and the mass of rich neutron matter of the star is 70% times m sub b times 30% times m sub s, which is equal to 21% times m sub b times m sub s. These two products are the same. The gravitational force that the black hole exerts on the star cancels out the repulsion force that it exerts on the star. Therefore, it is not necessary for the star to revolve around the black hole to prevent itself from falling into the black hole. In reality, stars and galactic spiral arms have to interact with not only its central black hole, but also the surrounding stars. For example, star 3 in this image is surrounded by star 1, star 2, star 4, and star 5. However, the theory of repulsion field believes that stars will find their own ways to adjust their ratios of rich neutron matter to poor neutron matter inside themselves, so that they can stay still in reference to each other and do not fall into their central black hole. In fact, it has been confirmed that galaxies are expanding. That means repulsion force is driving stars to move away from their central black holes. Further studies should be conducted to explain why stars are not falling into, but moving away from their central black holes.